Hi, I'm Seokhyun Hong, a master's student in Visual Media Lab, and the paper that I'm going to share today is Human Motion Diffusion Model, written by Tebet et al., and it was accepted in iClear 2023 as a spotlight paper, which means that it was a top 25% among the accepted papers. And as you can see from the title, this paper is about human motion generation using diffusion model. And the contents will be like this. So yeah, human motion generation is an important task because graphics industry like games and films always involve human motions, and other fields like robotics also do. And for this purpose, generic models on motion domain have been suggested, and they include variational autoencoders, normalizing flows, and GANs, which are the widely used generative models. And also the generated model for character animation includes the text-to-motion generation. Since the text is a simple but intuitive way to describe what users want to generate, so the text conditional or action conditional models have been proposed. But this paper is pointing out that previous works suffer from limited expressiveness and the low quality. And this is because the baseline model they adopted have some limited expressiveness. For example, with the same text or same action kick, there might be various motions like soccer kicks, karate kicks, capoeira kicks, but current methods cannot express this diversity. For example, here's an autoencoder and the input, and so the input X and the latent Z will be mapped on as one-to-one mapping, right? And another case, variation autoencoder will be mapped onto one-to-normal, and it can generate more diverse outputs than the vanilla autoencoder, but still it is not enough. And here comes the diffusion model. As you know, the diffusion model has much higher stochasticity than any other generative models, and it enables the model to generate diverse outputs. And as you can see here, diffusion model can generate diverse yet plausible results. And also, diffusion model can be conditioned on text. For example, you can generate a panda conducting a chemistry experiments, or Napoleon cats, or teddy bear on a skateboard in Times Squares. In this paper, diffusion model is adopted as a baseline model for motion generation, and they propose a few modifications on diffusion model to make it appropriate for motion data. And as you can see here, as the image is denoised to get closer to the real plausible image, the motion is denoised and it gets closer to the much plausible and natural results. So the contributions of this work include the architectural modifications in diffusion model specifically designed for motion data. And the second one is they propose a generic design that allows for different forms of conditioning, including text to motion, action to motion, and even unconditional generation. And the last one is they propose a generic design that enables different tasks, including motion completion and motion editing. So here's the methods. So as many of you already know, diffusion model consists of two steps. The first one is for process that progressively adds noise to the input, and it is denoted as Q here. And the other one is the reverse process that removes the noise from a noisy input, denoted as P here. And here, what the network learns is the reverse process, which means that how much noise to remove given a noisy input and a diffusion time step is what the network should learn. And another type of training strategy that this motion diffusion model uses is classifier-free guidance. I'm not going to deeply explain about it, but anyway, it's a type of conditional generation. And this figure shows that stronger guidance weight can generate less diverse but much plausible results. So you can think of these, there are 3 classes here, and as the guidance weight gets stronger, the generated outputs are less diverse but much plausible. And here are other examples. As the guidance weight gets larger, more plausible husky dogs are generated, but diverse is a bit less. And here are another examples. And based on those techniques, the motion diffusion model MDM's over structural looks like this. You can see that clip text encoder to allow for the text conditioned generation, and the architectural is mostly based on the transformer, which are purport to deal with sequential data. And specifically, the latent, the text latent vector and the diffusion timestep t are projected onto the same dimension, and they are added together, and it becomes a token to the transformer. And for the network, both the text prompt and the diffusion timestep t are conditional variables, because the model should generate different outputs given different text prompts and the different diffusion timestep, right? So they are both conditioned and added together. And the base architecture is transformer, which are good to deal with sequential data. So the motion data X is projected via a linear layer, and the positional embedding is added, goes through the transformer encoder and linear decoder, and the output is generated. And one thing you should note is that they predict the content, not the noise, which are different from the original DDPM. And actually, content prediction is nothing new because it appears in the DDPM paper. And as far as I know, DALI 2 is also using the content prediction. In this way, after the input is denoised, and it is diffused again, but one less diffusion time step with large T minus 1, and it goes and it is given as an input again with the reduced diffusion time step, and the content is predicted again and diffused again with one less diffusion steps. And it repeats until it arrives at the final step.
I have a question before you go further.
Yeah.
So in the previous slide, you mentioned guidance weight.
Yeah.
So where is it applied in this diagram?
That's a good question. So actually, guidance weight is not used in the training, but it is used as a inference stage, and I will talk about it later slides.
Okay.
So again, here are the loss function, and here's why content prediction is beneficial in motion domain. The author's proposal is that content prediction is beneficial, especially in the motion domain, because geometric laws like predicting the rotation, position, or velocity can facilitate the network to learn the geometric structure of the motion. And in the entire denoising step, all the x hat zeros are used for the geometric laws because it is a content prediction. And if it was a noise prediction, all the intermediate values are noise, which makes using geometric losses impossible because it is noise, not a motion. And so this L simple is just a simple content prediction loss and position loss for global joint positions using FK and the velocities and the foot loss to prevent the foot sliding.
Can you explain the content prediction loss again? I mean, all the other terms are making sense, but then this one, I'm not sure if I understand this.
So this simple L simple content prediction loss compares the predicted content and the original ground truth content.
Okay, so here the content means the position, velocity, and all other things are handled separately. So what is the content in this?
It might be different depending on the data set, but you can think of it like joint orientations or root positions, like the ground truth motion features.
So, okay, so in the next slide, the position and velocity and foot contact is handled separately. So separate from this, orientation of the joint angle is handled in this term.
Yeah, right.
Okay, and what else? Why in this case they don't say orientation term?
That's why. Yeah. So that's why here the X, the ground truth content, might be different depending on the data set. Some data set uses joint orientations for the features, but some others use joint positions or something other ones. So it might be different depending on the data set.
Okay, then the position in the next term is not the position of the joint, but instead it's like a position of the foot.
It's for all the joints.
All the joints.
Yeah.
Okay, so so I'm a bit confused by this. So in the second term, it deals with all the joint positions. Yeah, first term, depending on the situation, maybe the position can be included here, or sometimes it's not. So.
So maybe as far as I know, the data set that uses position as their data is representing like root relative local joint positions. And here the loss position uses the global joint positions. So they are a bit different.
Okay, second one is absolute value, and the first one is relative values.
Yeah.
Okay. Okay, for now.
Yep. And here's the and I said before, MDM uses classifier pre-guidance. And here the null means that there's no condition. And here S denotes the guidance vector, which the professor asked a few minutes ago. So here, as S gets larger, more plausible results will be generated while losing some diversity. So, and the results will be on the later slides. But users can determine the value of S during runtime to get some results they want to get. And MDM also can do editing like motion in-betweening with the same way of image in painting. So given a motion sequence, diffusion and denoising process is repeated by masking the parts to maintain. So here the orange parts are kept constant, maintained, and then here the blank white areas are generated through the diffusion model. And interesting thing is that this way also allows for the conditional inputs like text prompts. So text-guided editing is also possible. And here are the results. The overall results are like this. So they can generate diverse motion. And also text or action conditional is possible. And also the quality is quite good. They can generate some global positions and less foot sliding artifacts. And with the same text input, they can generate some diverse outputs. They look really different. And even with the same some ambiguous word kick, they can generate some diverse outputs.
So how is this diverse motion produced corresponding to? So you show, like, for instance, in this case, 3 different or same motion but different style. How do they choose this different style?
Actually,
is it randomly generated every time?
Yeah, that's just a random generation. So they're
okay. Yeah. So you cannot expect the same result once you have this result.
Yeah, right.
Okay, so every time it will be different.
Yeah, every time it was different.
Okay.
And here's the comparison to the previous methods in text to motion. So with the text prompt person walking in an S shape, the previous works look quite similar, but the results in MDM is quite more diverse than the previous works. And they can even generate some complex text prompts, like a text including multiple actions to do. And the quantitative results on the human ML3 test set shows that the MDM is generally outperforms previous methods. And one interesting thing is that using different text encoder like BERT doesn't affect much, which means that which text encoder to use is not a big problem in this architecture. And in another data set, it is still comparative to previous methods, as you can see here. And
I have a question regarding the notation in the previous slide. What's the arrow that goes to the right-hand side mean?
So here the arrow means that
yes, smaller the better, higher the better, right?
Yeah.
How about diversity, like sideways? What does that mean?
This one is, it is better to close to the real data.
Close to the real data.
Yeah.
Okay.
And the bold means that it is the best.
Okay.
And here's another comparison in action to motion with some ablations on geometric losses. And you can see that geometric loss is doing something good, and it looks quite much natural compared to the previous state-of-the-art action to motion model. And action to motion's quantitative results on this data set shows that MDM outperforms previous methods in this metrics. And in another data set, MDM is still quite comparable or outperforms the previous methods. And here are some examples in editing. So you can edit only some partial joints like arms And you can also do some in-betweening. So given the first and the last frames. And also you can do some text conditioned motion in-betweening. So with the same start and ending poses, given the text, the in-between poses are generated differently. And this table shows that the experiments on unconditional synthesis and the MODI got the best score since this model is carefully modeled for unconstrained settings, but still MDM has an advantage being a generalized generation model. And also, while it is not designed for unconditional synthesis, it is still better than another conditional generation model, Actor. So you can see that MDM is outperforming Actor in all the metrics. And additional experiments include user study and classifier-free scale sweep. So user study has shown that MDM outperforms the previous methods, except for the ground truth data. And the scale sweep experiment shows that guidance scale was best around 2.5. And as an appendix, the less diffusion steps were comparable to higher diffusion steps. So in most cases, in most diffusion papers, they use 1,000 diffusion steps, but in this case, 100 steps are the best option compared to the others. So it means that inference time can be 10 times faster than 1,000 steps. And it also indicates that large steps do not always imply better results, at least in the motion domain. So here's the contributions. So they proposed architectural modifications on diffusion model based on transformer and geometric laws via content prediction. And they propose some generic design that allows for different forms of conditioning and different tasks. So this is my presentation. And any questions?
The method seems to be working very nicely. Do they talk about limitation of this method?
Limitations. As far as I remember, there were no explicit limitation they were saying. Yeah. They didn't mention about their limitations.
I also had a question. It
Yeah.
was very interesting paper and very general. It was quite nice. You have very experience in this field. What do you think would be the future work? I mean, or how we can improve it if we want to do research on this field?
I think one problem on the motion generation is that, as the professor pointed out, the user cannot expect what to be generated. So user control is really limited, although they allow for text conditions or something high-level conditions, but users cannot expect which one would be generated. And although some users would want some accurate controls over the outputs, so overcoming those issues might be a good future work.
I have a question about the architecture again. Could you go to page 25, 26, where it has an overview of the network? Here, I think.
Yeah.
So text prompt and the time step goes into like the TK, and I believe the diffusion process is about diffusing the noise in every steps, and I wonder where does the noise comes in. I believe the
Is it?
input text prompt and the T is a condition, right?
Yeah.
So it should produce without this condition, right?
Yeah.
And I wonder where does the initial noise input
So
comes in.
actually the X here is the noise input. So noise is given as an input and the output is a predicted motion.
Okay, and on the right side of the image, it says diffuse, in the diffuse block, it says 0 direction with the t-1, and then
Yeah.
it's also 0 to t-2.
Yeah.
So could you also explain about this notation? Why does it go from 0 to?
So here X sub large T is, for example, diffused with 1,000 steps, and the predicted motion is something like predicted motion. And here diffuse from 0 to t-1 indicates that it goes the diffusion process for 999 steps. So, and it is given as an input again, and it the denoised output will be diffused again in 998 steps. So it is like gradually reducing the diffusion steps.
So in my understanding, it's first denoise it and then add noise again until the right before step, and then denoise it and then noise it like this iteratively.
Yeah, exactly.
Okay. I think now I kind of understand. And about the adding T and the text prompt, the notation seems to be the plus. Is it a concatenation or just element-wise summation?
Yeah, it is element-wise addition.
Okay. Is it the same as encoding the positional encoding?
You mean this?
Yeah.
Yeah, maybe.
Okay. And also, does it has some limited length of the motion? Like, can it produce any length of the motion?
I think that's a good question. I don't think it would be infinitely long, but the follow-up works of motion diffusion model is using some tricks to generate some longer sequences, like blending some the latent features or something like that. But yeah, for the answer for your question, it might not be infinite.
So, which means it has some ability to produce some divergent length motion, but it cannot produce infinite long motion, right?
Yeah, I think so, but I cannot guarantee that.
Okay. And for the last,
Yeah.
I'm sorry, I have too much question. About the motion, it said it's capable of producing diversity of certain motion, and I wonder how can it, what should I say, secure the quality of diversity. Like, you know, when you go to the example of producing a S-line walking thing, and I believe I remember that the MDM kind of, the middle one produced walking just diagonally, and it 아니구나. Sorry, maybe I missed it, but yeah,
But
I wonder how it can control the quality of the diversity. You know, when you give an input of person walking in an S shape, it can just slightly walk as like wiggly shape, or it can, you know, move in as in very dynamical. 뭐야 저거 아무튼, you know.
I think the controlling the guidance weight might be a way to solve it, but there can be trade-off between the quality and diversity. Yeah.
Thank you.
I have a question.
Yeah.
So in terms of guidance scale, when we scale down the guidance scale,
Yeah.
I know that it means we are attenuate the influence of conditioning signal.
Yeah.
So we can produce various type of motion. Right?
Yeah.
So is it a plausible motion or just various motion that is not what we desire? Like there is some, I mean, when we scale down the guidance scale, we can produce various motions, but it is not plausible motion because it attenuates the influence of the conditioning signal.
Yeah.
So the result, the motion is like something is ambiguous or 그러니까 그 모션이 뭔가 is it a plausible motion? Like no, 그러니까 움직임이 약간 좀 이상하다던가. 그냥 다양한 모션인데.
Does the quality grade if you use low value of guidance weight?
Yeah. Yes.
Unfortunately, they didn't show the different results depending on different guidance weights. So yeah, I have no idea about it. I'm sorry.
It's okay. Thank you.
Can I also add a comment?
Yeah.
You told me one of the things future direction can be make editing, user editing for the motion.
Yeah.
And the thing is that now you give a text as an input condition.
Yeah.
And you can also, we have a paper in our lab, a sketch to motion. They give the root position and the hand positions, and it estimates the output motion. Here, what do you think if as input, we also give the root positions and hand positions during the training?
Yeah.
But in the test time, we gave them as a clue, as an input to the network. For example, I want to complete this motion in a S shape, but the hands are moving with this pattern in the 3D space.
You mean the like trajectory of the root and hands, right?
Yeah. If we add that during the training time, we can use it in the testing time as a guidance that user gives.
Oh yeah, that might be a really great work, because sketch is kind of really accurate and explicit user guide, while the text is kind of ambiguous. I think that's good.
Oh, thank you. So during the training, we will record the root position and hand position because we have in the data set, we give it as input. And that in friends time, we just give the positions as a clue, as input, and it helps to generate input. Okay, thank you.
The combination of diffusion model with the sketch input.
Yeah.
Thank you. Yeah, awesome.
Oh yeah, it would be really nice.
I have a question. How can they give the condition like sketch, or if the in-between task, how they give the conditional process to the network?
So I think, I'm sorry. So here, C token is given as a conditional token, right? So this implies something conditional information that the generated output should refer to, or I think we can use some other methods like cross attention or something else to make the output to refer to other other modalities. Actually, the follow-up works of diffusion model, motion diffusion model on the dance generation is using cross attention with motion and music features.
So instead of the text prompt and clip, we can use some other network or like other condition to give the conditions.
Yeah, the methods
So-
really, yeah.
That is great. Thank you for clear explanation.
Any other questions? If not, I will finish sharing my screen. Thank you for listening.